Hello, listeners. This is Mike, your host. If you are enjoying these archive episodes, please consider supporting the podcast by going to the homepage, spacerockethistory.com, and clicking on the orange donate button or the Patreon link. Hopefully, with your support, I can continue to release these archive episodes. Thanks. Hello and welcome. This is Michael Annis, and you're listening to episode 176 of the Space Rocket History Podcast. And now, the first test flight of the Soviet N-1. If you haven't done so already, I recommend that you listen to episodes 174 and 175, the early history of the N-1, before you listen to this episode. Before we get to the flight, I wanted to review the specs of the N-1 and compare it to the Saturn V. The fully equipped N-1 stood 105 meters, or 344 feet tall, with its L-3 payload. The N-1 L-3 combination had 5 stages. The first 3 on the N-1 were for insertion into low Earth parking orbit, and the other 2 were associated with the L-3 complex and were used for translunar injection and lunar orbit insertion. Fully loaded and fueled, the N-1 L-3 weighed 2,750 metric tons, or 6,062,000 pounds. The lower 3 stages were shaped to produce a single frustum, 17 meters or 56 feet wide at the base. The L-3 section was mostly cylindrical and was carried inside a shroud 3.5 meters or 11 feet wide. The conical shaping of the lower stages was due to the arrangement of the tanks within them. A smaller spherical kerosene tank on top of the larger liquid oxygen tank below. The first stage, called Block A, was powered by 30 NK-15 engines arranged in 2 rings. The main ring of 24 at the outer edge of the booster, and the core propulsion system consisting of the inner 6 engines at about half that diameter. The engines were the first ever staged combustion cycle engines. The control system was primarily based on differential throttling of the engines of the outer ring for pitch and yaw. The inner ring system was not used for control. The Block A also included 4 grid fins, which were later used on Soviet air-to-air missile designs. In total, the Block A produced 45,400 kilonewtons, or 10,200,000 pound force of thrust. This exceeded the 33,700 kilonewton, or 7.6 million pound force thrust of the Saturn V. But the Saturn V used higher specific impulse liquid hydrogen fuel in the second and third stages, which eliminated one of the stages needed to get to translunar injection, thus saving weight. The second stage, called Block B, was powered by 8 NK-15V engines arranged in a single ring. The only major difference between the NK-15 and the NK-15V was the engine bell and various tunings for air start and high altitude performance. The upper stage, called Block V, mounted 4 smaller NK-21 engines in a square pattern. The control system was called CORD, K-O-R-D, and it stood for Control of Rocket Engines. The CORD system controlled the differential thrusting of the outer ring of 24 inches on the first stage for pitch and yaw attitude control by throttling them appropriately, and it also shut down malfunctioning engines situated opposite to each other. This was to negate the pitch or yaw movement diametrically opposing engines in the outer ring would generate, thus maintaining a symmetrical thrust. The N1 could continue to fly even if it lost some engines. For example, the Block A first stage could perform nominally with 2 pairs of opposing engines shut down. In other words, with 26 of the 30 engines working. Block B, the second stage, could continue with 1 pair of opposing engines shut down, which means 6 of the 8 engines working. And the third stage, Block V, could continue with 1 engine shut down, or 3 of the 4 engines functioning. Now, a little comparison with the Saturn V. At 105 meters, the N1L3 was slightly shorter and more slender than the Apollo Saturn V. But the N1 was wider at the base, 17 meters versus 10 meters for the Saturn V. The N1 produced more thrust in each of its 3 stages than the Saturn V. It also produced more total impulse in its first 4 stages than the Saturn V did in its 3. The N1 was intended to place 95 metric tons of payload into low Earth orbit, whereas the Saturn V placed roughly 45 tons of the Apollo spacecraft plus 74 tons of fuel used for translunar injection. So the Saturn V put roughly 119 metric tons into low Earth orbit. Okay, another difference. With the N1L3, the translunar injection of the 23.5 metric ton payload was provided by the 4th stage. But with the Saturn V, translunar injection was accomplished with the 3rd stage. Another difference was the type of fuel used. The N1L3 used only kerosene-based rocket fuel in all 3 of its stages, while the Saturn V used liquid hydrogen to fuel its 2nd and 3rd stages, which yielded an overall performance advantage due to the higher specific impulse. The N1 also wasted available propellant volume by using spherical propellant tanks under its conical-shaped external skin, while the Saturn V used most of its available cylindrical skin volume to house capsule-shaped hydrogen and oxygen tanks, with the old common bulkhead between the tanks in the 2nd and 3rd stages. Saturn V also had a superior reliability record. It never lost a payload in 2 development flights and 11 operational launches, while 4 N1 development launches all resulted in failure with 2 payload losses. Now I want to move on to the flight plan for the first launch. The N1 rocket was to carry a simplified prototype of the L3 lunar complex. It was called 7K L1S, which was about 30% lighter than the rocket's standard payload for manned lunar landing. The payload section was fashioned out of a 7K L1 spacecraft designed to fly around the moon. To give the spacecraft additional maneuverability during a more complex mission, it was upgraded with a custom-built attitude control unit mounted on the top of the vehicle. The flight plan called for inserting this improvised spacecraft into lunar orbit rather than simply swinging it behind the moon. Inside its descent capsule, the spacecraft was reportedly carrying powerful cameras intended for photographing lunar surfaces and delivering exposed film back to Earth. According to most sources, the unmanned crew capsule was equipped with an operational emergency escape rocket. Since the main digital computer for the N1L3 complex wasn't ready, the flight would be controlled with a makeshift analog system. Moreover, the NK-15V engines on the second stage of the rocket were lacking their nozzle extensions. Both of these fallback solutions degraded the capabilities of the rocket. However, with a reduced payload mass, all critical phases of the flight could be tested. The powered flight of the rocket was to last for 597 seconds, placing the Block G and Block D stages along with their spacecraft payload into parking orbit around the Earth. Block G would then fire its engine, sending the payload on a 3.5-day trip toward the moon, and separate. Block D would then make a necessary course correction and then fire again to ease the spacecraft into lunar orbit, where the stack was to spend another 2.5 or 3.5 days. Block D then would fire for the third time, sending the spacecraft back toward Earth. In case of a complete success of the first and following launches, the actual lunar landing of Soviet cosmonauts was still likely 2 years away due to the need to certify all the other components of the L3 complex, such as the LOK spacecraft and the LK lunar lander. And, of course, there was still testing required for all phases of the flight. Moving along, on February 9, 1969, a meeting of the State Commission in Tyuratam was held with the goal of confirming the official launch date for the first N1 rocket and clearing it for rollout to the launch pad on the same day. The majority of civilian members of the commission pressed for a launch as soon as possible. After all, with the lack of test facilities for a fully assembled rocket, only an actual launch could provide real-time data and reveal problems. That's how it had always been done in the Soviet Union from the dawn of the space era, except that now the rocket was much more expensive and required so much more time to build. Of course, mid-level telemetry specialists and military test officers in Tyuratam were well aware of numerous unsolved issues with the vehicle. Many problems were apparently revealed even during the final integration test, which had just recently been completed in the assembly building. Not coincidentally, the test officers who conducted these tests were excluded from the group of officials whose signature were required on the final certification documents. However, during the meeting on February 9th, General Kurushin, the military chief at Tyuratam Test Range, made a shocking call not to launch, citing numerous problems in the launch equipment and the rocket itself. Surprised by the opposition to the launch at such a high level, the Minister of General Machine Building, Sergei Afanasyev, called for a pause in the meeting. During the break, Afanasyev, Vasily Mishin, and the Central Committee's representative, Stroganov, along with other industry officials, pressed General Kurushin and his military superiors to reconsider. Marshal Krylov, the highest military officer at the meeting, finally surrendered on the condition that all the issues cited by General Kurushin would be resolved before launch. In the end, the rocket was cleared to make its monumental trip to the launch pad. The fueling of the payload section with its toxic and corrosive propellants was scheduled to start on February 13th, marking the so-called irreversible operations, after which it would be very difficult to cancel the flight. The launch was set for February 18th. In addition, 3 more N-1 rockets were scheduled to fly in April, June, and November of 1969, even though the L-3 lunar complex was not expected to be ready for a manned mission until the following year. All right, let's talk a little bit about the politics surrounding the launch. In preparation for the first N-1 launch, the Central Research Institute of Machine Building was assigned the politically sensitive task of putting an actual number on the expected reliability of the N-1L3. The Institute made these estimates based on a very detailed failure record of 30 Soviet missiles and space launch vehicles. This allowed the Institute to predict that the probability for the first N-1 mission to complete all its tasks barely exceeded 1%. Even with the most optimistic assumptions about the performance of all its stages, the N-1 only had 16 out of 100 chances to fulfill its mission. The head of the Central Research Institute of Machine Building was Yuri Mazorin, and he knew it would be political suicide to officially present such grim statistics. Still trying to keep a semblance of scientific approach, he ordered a recalculation of the data minus any considerations of failure caused by lack of quality control and by operational errors. Only failures rooted in previously unknown phenomena would now be factored in. After all the massaging of the data, the Institute arrived at a 67% probability of the first N-1 completing its task, with a margin of error spanning from 38 to 90%. Mazorin, now believing that he finally had politically acceptable results, announced his 67% chance of success at the State Commission meeting on the eve of the first launch. However, his optimistic prognosis was met with a graveyard silence. Nikolai Palyugin, the head of Flight Control Systems Development, was the first to utter a word. While admitting that nobody had the right to certify the vehicle for launch with such a high probability of failure, he proposed to dismiss the whole exercise of relying on historical record. Palyugin argued that only personal assurances from all top managers about flawless operation of their systems could serve as a legitimate criterion in a launch decision. The majority agreed, not the least of whom was Mazorin, because his organization would no longer be held responsible for a possible disaster. With the preliminaries finished, we will move on to the launch. The first 28-day-long N-1 countdown began in January of 1969 with the rollout of the N-1 to the pad. Vasily Mishin personally led 2,300 technicians in around-the-clock shifts to prepare the vehicle for its first flight. 50 tank cars of propellant were required to fuel the booster. Not surprisingly, as soon as the rocket was powered up on the launch pad, its telemetry revealed numerous problems. For several weeks, military officers and their civilian colleagues struggled to prepare the vehicle and fix problems, often working dozens of meters above the ground on the open surface tower in a bitter cold minus 30 degrees Celsius and winds reaching 12 meters per second. Finally, on the morning of February 21st, all the population of the N-1 assembly area and a residential area situated just south of the launch pad was ordered to evacuate, The giant structure then rolled away, leaving the dark gray rocket with a white payload fairing towering under the sunny skies. The weather was extremely cold, with temperatures falling to minus 44 degrees Celsius and stormy winds. In the fortified firing control room, the commander of the 6th Directorate took the firing command position at the main periscope. The liftoff button was pressed at 12:17 and 55 seconds Moscow time. The 30 engines of the first stage needed 12 seconds to develop the thrust necessary to lift the giant rocket off the ground. At 12:18 and 7 seconds, the first N-1 vehicle lifted off. As it was rising above the launch pad, telemetry officers reported shutdown of 2 engines. However, the rocket, emitting a long trail of fire and black smoke, continued flying seemingly stable. The deafening roar reached onlookers miles away and then started subsiding as the rocket was receding from view. After about a minute, the bright glow of its engines suddenly faltered. The loudspeaker announcements of the flight milestones also stopped. For a few seconds, the rocket continued climbing slowly, and then, to the horror of observers, started descending down, seemingly in one piece. A faraway flash of light confirmed its impact. In less than 2 minutes, several years of effort by engineers and workers had been turned into heaps of twisted and burned metal. In the immediate aftermath of the accident, most witnesses could only guess what had made the rocket suddenly stop firing all its engines. The monitoring data showed that the vehicle reached an altitude of 14 kilometers and crashed 183 seconds after liftoff. At least one source claimed that the emergency escape system at the top of the rocket had fired successfully, pulling away the unmanned spacecraft and enabling its descent module to safely land under a parachute. Very preliminary information showed that in the first seconds of the flight, engine number 12 and number 24 had shut down. The remaining 28 engines of the first stage ceased operation at T plus 68.7 seconds. While officials were still in the firing bunker, OKB-1 chief designer Mishin was quick to lay blame on the developer of the power supply system. Mishin claimed that turbo generators producing electricity on board had failed. After all, what else could stop all engines of the first stage at once? Trying not to jump to conclusions, Sergei Afanasyev appointed Mishin to lead the investigative commission. A helicopter and ground teams were sent to recover the debris scattered along the flight. The main crash site of the rocket was found in the snow-covered steep 52 kilometers northeast from the launch pad. Smaller pieces of the rocket apparently fell elsewhere. Meanwhile, engineers started deciphering the telemetry data. The telemetry confirmed that the power supply system kept operating all the way until impact. Search teams also recovered the power supply system, which was then rushed to the manufacturer, where it was successfully restarted, thus proving Mishin wrong. It was not the power supply that caused the problem. Early data also pointed at a fire in the tail section of the first stage. But the investigation quickly focused on the behavior of the Cord rocket control system, which had the capability to shut down individual engines. Chief Designer Mishin ordered the creation of a small subcommission on the Cord system, appointing Chertok as its head. After 3 days, telemetry specialists confirmed that all the engines of the first stage had been deactivated by the Cord system. By the beginning of March 1969, after a repeated thorough analysis of telemetry tapes, followed by many discussions and calculations, a true picture of the failure started emerging. This is what happened. At 0.34 seconds after liftoff, as the engines reached full thrust, the Chord system issued a faulty command to shut down engine number 12. This command was triggered by electric interference originating in the Chord's wiring located near engine number 12, when pyrotechnics blew up valves opening the propellant supply. The oversensitive Chord system interpreted the resulting power surge in its circuitry as a sign that the turbopump in engine number 12 was spinning faster than it was supposed to and was about to explode. According to its algorithm, the Chord also turned off engine number 24 on the opposite side of the rocket in order to maintain symmetry of the thrust. However, other investigators soon brought additional pieces of the puzzle in the complex picture of the failure, shifting the root cause of the problem from Chord to the engines themselves. As it turned out, 6 seconds after liftoff, high-frequency vibrations had torn off a gas pressure measuring pipe located downstream from the turbopump in engine number 2. To make matters worse, at T plus 25 seconds, a pipe for measuring fuel pressure before the gas generator had also broken off, spewing kerosene into the guts of the rocket. Inevitably, leaking gas with a temperature of 340 degrees had ignited the kerosene and started a massive fire in the tail section of the rocket 55 seconds after the liftoff. The flames had destroyed insulation on power supply cables, which were running alongside Chord's cables. As a result, a low-frequency signal of 1,000 Hz had leaked into the Chord sensors and had been interpreted as out-of-limit pulsations in gas generators inside the turbopumps of the propulsion system. At this time, a 25-volt signal, which exceeded allowable voltage by 10 volts, had traveled across the entire web of the Chord network. The Chord had responded by shutting down all 28 engines at 68.7 seconds after liftoff. Moreover, the faulty command had also traveled up to the second and third stages of the rocket, leaving the giant vehicle completely paralyzed. On March 7th, the investigative team presented their findings to the rest of the N1 engineering team. The root cause of the failure in the first N1 launch was thus declared to be resolved. Not surprisingly, the program officials pressed for another attempt as soon as possible. Thanks for listening to this archive episode of the Space Rocket History Podcast. If you are financially able, please support the podcast by going to the homepage, spacerockethistory.com, and clicking on the orange Donate button or the Patreon link. Thanks.